Okay, so let's get started. We're continuing our journey through the network layers. So today we will finish off talking about bridges that connects local area networks together in a transparent way, and then go over to talk a little bit about Wi-Fi. And the reason why we talk about Wi-Fi is to see how the things that we have learned from a more generic point of view, how they are actually put together into a real system. So it's kind of interesting to see, what techniques are used here. Okay, so first of all, we talked about medium access. And one thing in medium access is that we would like to share a channel. And actually, a channel is then split up into resources that are handed out to the various users. So a channel resource, what is that? Well, it's basically an area in the time frequency plane that we need to somehow share. And one way to do that is to do channelization, that is to split up this channel resource in either time or frequency or both, and then hand out these resources to various users who can then use it without fearing a collision. So this is called a fixed channelization scheme. So the main ways to do that is to split up time into time slots. So each user can use the entire system bandwidth, but only under limited time. We can do frequency division, which means that a user can use the channel at any time, but only in its allotted frequency channel. So the frequency channels are not overlapping. And then there is this strange sort of hybrid. It's not really a hybrid, but it's another way to sharing channel resources. And that is to use waveforms, different waveforms for different users. And these waveforms overlap in both time and frequency, or one of them at least. But then they can be separated at the receivers, and this is possible if these waveforms that we hand out to the various users are approximately orthogonal, because then by using a matched filter to that specific waveform, we filter out the other waveforms. So the question is which one of these one should choose, TDMA, FDMA, or CDMA. TD for time division, FD for frequency division, CD for code division, MA for multiple access. And it turns out that there is from a top level, there is no reason to choose one over the others. So it has basically to do with implementation issues. They can be shown to have the same capacity under ideal circumstances. So what are ideal circumstances? Well, it's when we have perfect time and frequency synchronization, where there is a negligible propagation delay and so forth. In practice, this is not true, right? So depending on the system you have, you might want to have TDMA rather than FDMA, or the other way around. Or if you use a hybrid, you need to design how much time, what is the width of the time slot, and what is the frequency content of the time frequency slot. And then also what is the appropriate guard intervals between these resources. So, but that's basically, that has to be done from case to case. Then we started to talk about local area networks. And in principle, they are physical small networks that share a medium. Broadcast here essentially means that when one station which is hooked up on the network, the local area network, transmits something, this is picked up or can be heard by all other stations attached to the local area network. So these LAN protocols, they are in the OSI model, they are in the link layer. And if we want to look at a practical remember that the OSI model is more like a theoretical construction on how to think about protocols. There are no real protocols here which are in practical use. So the protocols which are in practical use are, for instance, from the IEEE 802 family of standards. There are, of course, other ones that are used, but we talked mainly about this IEEE 802 model. And then for the IEEE, they split up the protocol stack in the following way. At the bottom we have the physical layer as before, and then they have a number of medium access control layers and one unifying layer on top of all of these MACs, and it's called the logical link control. Of the MAC layers that we talked about, we briefly touched on, or we talked a little bit about this 802.3, which is sometimes also called Ethernet. Today we will talk about this, and the other ones we won't really talk about. They are, of course, different for different purposes, but anyways. So 802.3 is sometimes called Ethernet. It's a very common LAN protocol. There is a slightly different and earlier version of this, which is called DIX Ethernet or Ethernet 2. It's a little bit strange that Ethernet 2 is actually before Ethernet, right? But you know, it's just the way it is, I guess. And this is heavily used in already now also. Okay. Luckily, Ethernet and Ethernet 2 or DIX Ethernet, they are very small differences. So a network interface card can handle both of them with no big problems, really. Okay. So this 802.3, what is that? It uses carrier sense multiple access with collision detection. And it's one persistent CSMA with truncated binary exponential backoff. Okay, so there's a lot of words there. So what it means is that we do carrier sensing. So essentially we listen to the medium. If the medium is idle, then we transmit. And then we do collision detection, which means that during the first time of the first period of the transmission, we check for collisions. And if there is a collision, then we stop to transmit, and then we back off. If one wants to access the medium and the medium is busy, we wait until the medium becomes idle and then transmit. That's the persistent part of it. If a collision is detected, then, as I said, we stop transmitting and we wait the random backoff time. And this random backoff time depends, is a number of slots. It's R times T slot, where R is a random integer, so it's chosen between 0 and 2 to the power of k minus 1, where k here is the retransmission attempt. So we start with k. We start with okay. So here's the formula. So k is equal to n, the retransmission attempt, until we reach the 10th one, and then we keep k equals to 10. So k is equal to n when n is less or equal to 10, and then 10 when n is greater than 10, like this. Okay, so that's what this equation says. Okay, and the reason for increasing the contention, this backup window, as we do more and more retransmissions, is because we do retransmissions are caused by collisions, and collisions are caused by a number of stations want to access the network at the same time. However, we don't know how many, so it's hard to have a fixed contention window which is optimal for all situations. So in the beginning we use a small window to be more optimistic that there is not so much contention for the channel, and then we can get short delays. But if we get repeated collisions, then we realize that there are many nodes wants to access the medium at the same time, and therefore we need to be more relaxed in our backoff. More relaxed meaning that we can wait longer times also. So the purpose of this binary exponential backoff is to reduce the probability of repeated collisions, okay? But at the same time keep delay under control. The smaller the values of R can be, the less delays we have. Okay. All right. Then we switched over to talking about bridges or switches. So this is a switch, for instance, and this is used to interconnect several Ethernet networks together, right? So they are, in general, they're used to connect local area networks. in a way such that the stations which are attached to the local area networks don't see the bridges at all. For the stations which are attached, they just see a bigger local area network, even though the physical ones are smaller. So we create a big logical local area network out of a number of smaller physical local area networks. And bridges, they create their forwarding tables by something called backwards learning. And that is, the bridges look at the traffic on the attached local area networks and figure out what stations are attached to that network. And by doing that, it knows where to forward frames. Okay, so the purpose of a bridge is to move frames from the attached local area networks to the right local area networks. And the right local area network is where the destination is attached to. Okay, so we will see a little bit more about that today. Okay, so let's talk about bridges and finish that off, and then move over to Wi-Fi. Are there any questions so far? No? Okay. So here we have an example where we have a number of local area networks, 1, 2, 3, and 4. And these are connected with bridges. So we have one here, 1, 2, 3, 4, 5 bridges. And the adaptive learning or backwards learning that we talked about yesterday, the last time we met, only works if this topology don't have loops. So what is a loop? Well, a loop is when data can go from one local area network to another and then back through another bridge. Okay, so here we have one loop, and here we also have one loop. So data can go from 3 to 2 up to 1 down here and then end up here. And the problem with this is that frames can start to circulate here and never die. Okay, so they keep on spinning around here, and then the bridges get overloaded, and bad things happen. So there is another loop here, by the way, also from 4 to 3 up to down here and then back to 4. Okay, so we want to avoid this, and one way to avoid it is, of course, to never connect these bridges to these networks to start with, right? But the problem is that humans do this, right, and they make mistakes. And also, there could be a reason to have two bridges connecting, say, LAN 1 and LAN 2 together. Why would we like to have this sometimes? Can you guess?
Reliability.
Yeah. Exactly, reliability. So if B1 fails, then we have a backup in B2 here. Right. Okay, so what we want to do then is to get rid of these loops. And then what we want to do then is essentially to figure out which of these connections to have active and which connections to cross out. Cross out temporarily until, for instance, we could have it like this, that we only enable bridge 1 here to connect LAN 1 and 2. So these are connected, and these are then disabled. Okay, and then when B1 fails, then we reconnect these dynamically, right? So that's something that we would like to achieve, and there is a way to do that automatically without human intervention through something called the spanning tree algorithm. Okay, so we'll see how to do that. So what we would like to do is to make this topology, which has these loops, into a topology where we don't have loops. And we would like to have such a topology is called a tree. And we would like to have a spanning tree, meaning that all the local area networks are connected to each other somehow, but in a tree fashion. Okay, so here's the general idea. What we want to do is to make the bridges have specific roles in a network. So we would like to one bridge out in this network, one unique bridge, to be the root bridge, so the root of the tree. And we select the root bridge as the bridge with the lowest ID. I mean, you can do this in an arbitrary way, but let's use the ID of the bridge as the deciding factor here. Okay, so once we have done that, number one, we look in our network here. Which one here is the root bridge, by the way? B1, right? It has the lowest ID. 1 is the ID. Okay, and the second thing we want to do that is that for all bridges except the root bridge, we would like to determine the root port. Okay, what is the root port? It's the port of the bridge which is closest to the root. And what do we mean by closest? Well, it's the port with the least cost path to the root bridge. Okay, and so what is the cost? Well, going over a local area network has a certain cost associated with it. So the path goes over a number of local area networks, and the total cost is the sum of all the cost of all the local area networks we pass. We'll see an example later on. Okay, but anyways, each port has a certain cost associated with it, and the cost is the cost of the path to the root. And then for each local area networks, we select one bridge, which is called the designated bridge, and its designated port. Okay, so what is the designated bridge? Well, it's the bridge which has the least cost path from the local area network to the root bridge. And the designated port is the port that connects the local area network to that bridge. Okay, again, we will see an example of this. So these are still definitions, maybe a little bit hard to understand exactly what they mean. Number 4 in the process is that we put all the root ports and all the designated ports, they are put in a forwarding state, so they are made active. Okay, and these are ports that are allowed to receive and transmit frames. Okay, and all other ports are put in a blocking state, and they are not used temporarily. Okay, and then this is a dynamic process, so if something fails or we connect in we put in a new switch or whatever, then everything gets reconfigured dynamically without human intervention. Okay, so let's see an example on how to do that. So we already now know that B1 is the root bridge. But before, okay, so we have here the bridge IDs are the numbers inside the colored boxes here. And for bridge number 3, it happens to have 3 ports, 1, 2, and 3. And those also have numbers. Okay. So what we want to do is to select the root bridge. And we already know that this one will be the root bridge. Okay. So this is now the root. And then number 2 is we would like to figure out the root ports. Okay. And the root port, there is one per bridge, for every bridge except the root bridge. And we would like then to for instance, B2, let's say B3 here, has 3 ports. We know that this is the root bridge. And so which port is the root port? Well, this one has a cost 1 to get to the bridge because it goes over 1 LAN. This bridge, this port has 1 LAN, 2 LANs before it gets to the root bridge. So it has cost 2. This one has 1, 2, 3 to get to the root. Okay. So out of these 3 ports, number 1 here is the best in the sense that it has the least cost path to the root bridge. Okay. So this will then become the root. And we repeat that for all the bridges. For B2, it has 2 ports. And the cost to go from here to the root is 1. The cost to go from here to the root is also 1. Okay, so when we have a tie here, we pick the port with the lowest ID. Okay, so in this case, it's going to be port number 1. Here it's going to be port number 1 again, because it was pretty obvious. For this one, it's also obvious that this is the best path. This one is more costly. And for B5, which one would it be? Could it be this one, 1, 2, or is it 1, 2? Okay, so there is a tie. Which one will we select here? Which port?
1.
1, exactly. So this will be then the root port. Okay, so now we're done 1 and 2. Number 3 is to select the designated bridge and port for each local area networks. So now we need to do that for LAN number 1, LAN number 2, LAN number 3, and LAN number 4. Okay. So the what is the designated port? It's the it is the designated bridge and designated port. What is that? It is the bridge and the port which is closest to the root. Okay. So for LAN 1 it's pretty obvious since the root is attached to LAN number 1. So the designated port and designated bridge will be the root bridge in this case. For LAN number 2, that will also be the case because it's directly attached to the root. But if we look at LAN number 3, we have LAN number 3 has 3 choices for designated bridge. This one, and this one. So which one should we pick here? Well, we should pick the bridge which is closest to the root. So which one would that be? It could be B3 or B4. Okay, so which one? Because they have the same, it takes one LAN to get to the bridge, sorry, to the root for both B3 and B4. Which one should we choose?
Lowest number.
Exactly. So this would be then the designated bridge for LAN number 3. And for LAN number 4, which one should we choose? B3 again, yeah. Okay, so let's see if that actually turned out to be the case here. Yeah, so we see that for the purple LAN 3 here, this is the designated bridge. As we said, we tied, it was a tiebreaker, and that was the bridge ID. For 4 here, it's also this one. Okay, so now we have selected designated ports and designated bridges for all the local area networks. And now we're done. Okay, so what we do then is we put all the root ports and designated ports, we connect them somehow, we make them active. So for bridge number 1, we have a designated port here and a designated port here, so these are made active. For bridge number 2, we had the root port, but it was not the designated port here. So the connection here was somehow logically removed, right? It's still there physically, but at the moment we don't use it. For bridge number 4, it's the same thing. We crossed out that one. For bridge number 5, we crossed out this one. And it turned out for bridge number 3, all of them are active. Okay, we have one root port and 2 designated ports. So B3 here is serving both LAN 3 and LAN 4. Okay, and now we don't have any loops left. Okay, questions? Okay, so how do we do this in, we did this by hand right now, by just following the rules, and it was pretty easy because we knew what the topology looked like. But the problem is, of course, that these bridges have no idea what the topology is, because they don't have a network map. So they need to self-organize themselves into this topology. Okay? And they want to do that without user intervention, without human operation, and also without any configuration files or whatever. They just need to figure this one out. So when I connect a new switch to this switch will then learn its role in the network by communicating with the other switches or bridges in the network. So this looks like, is this difficult or not? Well, at the moment it seems maybe this is a very difficult problem, but it actually turned out that it's not so bad. So we can form a protocol for doing this. So let's just go through the protocol to get a flavor for how a distributed algorithm can self-organize into this type of topology. Okay. Okay, and the protocol is called the spanning tree protocol. So a spanning tree is found by the bridges themselves, and they do that by interchanging special packets called bridge PDUs, okay, packet data units, so BPDUs. Okay. And these PDUs are somehow the state of the bridge. So bridge maintains this a bridge PDU, and it stores it, and it uses that to transmit to the other bridges. So each bridge transmits its current guess on which bridge is the root bridge. So this bridge PDU consists of three parts. First, the ID or the transmitting bridge, and then the root bridge ID, which is the current guess by this bridge what the root bridge ID is, and then what is the cost for the transmitting bridge to reach the root bridge. And the cost here is the sum of the long cost on the path from to the root bridge. And these long costs, we said previously that they were the same for all the local area networks. That might not be the case in practice, because typically they are different depending on the data rate over the LAN. So the higher the data rate of the LAN, the least costly it is to transfer over that LAN. So we prefer to go over high-speed LANs than slow-speed LANs. Okay. So I said that the bridge stores these BPDUs, and it stores the best one it's seen so far. So how do we compare PDUs with each other? Well, to compare the PDU X1, R1, C1, which means that this is the PDU stored by bridge X1, and it believes that R1 is the root, and it has a path of cost C1 to the root. And then there is another bridge X2. It believes that R2 is the root, and it has a path of cost C2 to the root. What we do then is we compare these two in order. And the first priority is to select the root ID.
A question for R2 there. Isn't like the root one always like the small thing? Does that believe that some link has been like removed or something?
So hold that question a little bit. I think it will be obvious later on, because here, the idea is that finally the root is the bridge with the lowest ID, which is connected to the whole topology. But at the beginning, the bridges have no idea about that. So it will dynamically be updated until it figures out which bridge has the lowest ID that's connected to the overall topology. Right? But at the beginning, they have no idea. Right? So when I connect this it has no idea. It knows its own ID, right? But nobody else's at the moment. It has to figure this one out. Okay. But anyway, so when comparing these BPDUs with each other, the first priority is to look at the root. Okay. So if for instance, we select the BPDU with the lowest bridge ID. So we compare R1 and R2. So if R1 is less than R2, then this is better PDU than this one. Okay, now if R1 happens to be equal to R2, the second priority is to pick the one which has the lowest cost to the root. Okay, and if that also happens to be the same, that that the costs are equal, the roots are the same and the costs are the equals, then we pick the one with the smallest ID. So the third order of priority is the root ID of the transmitting one. Okay. So So, for instance, if we would like to compare 1 to 0 with 2, 1, 0, which one is the best here? 2, 1, 0. So this one is the best. Or is it this one? Is it this one or this one? Okay, so, well, maybe you don't remember this, but the BPDU is transmitting bridge ID, route ID, cost to root. Okay, so in this case, 210 is better than 120 because 1 is less than 2. Okay, so this was the selection in this case. Now suppose we have the 1, 3, 2 and 2, 3, 1. Then we see that they both think bridge number 3 is the root. Okay. However, the first BPDU has a cost 2 and the second has a cost 1 to the bridge. So which one should we choose? 2, 3, 1. Yeah, exactly. So here, this is the winner. And it's simply because 2 is greater than 1, even though 3 is equal to 3. And here it's because 1 is less than 2. Okay, and then of course the third case would be something like this, that we have 1, 3, 2, and then 2, 3, 2, like this. Okay, and then we see that 2 is equal to 2, 3 is equal to 3, and therefore we select the best one based on the ID. So 1 is less than 2, so in this case this is the winner. Okay, questions so far? Okay, so now we know how to compare these bridge PDUs with each other. Oops, no, I want to call it that. Okay, with each other. So how are we going to use this in the protocol? Well, here is the description of the protocol. It's a little bit long, but it's actually not so complicated, but it's we'll see. We'll make a short example to maybe clear this up. So at the beginning, what do we do when we start, when we know nothing? And with we, I mean a bridge here. So suppose I connect this to the network. What does it do? What PDU should we store in this one? Well, let's be optimistic, right? Let's think we're the king of the world and be the root bridge. So at power up, all the bridges believe that they are the root. Okay. So the initial PDU for root number x is xx0. Okay, it exits its own ID. It believes that I am the root. If I'm x, I believe I'm the root, and the cost to come to me is 0 because I'm the root. Okay. So then we transmit this out on all our ports to inform the rest of the world that we are the king of the world, right? We are the root. So please obey me, right? Now somebody else might disagree, right? Because all the other ones also think they are the root. So the key thing is that if you hear something on this cable that tells that some other switch is the root, and that root actually has a lower ID than my own ID, sorry, then I lost, right? Then I'm not the root. But then I know, okay, so then I say, okay, maybe this guy is the root, and I update the bridge PDU to reflect that. And then maybe at some later time, I hear on this cable, oh, there's even a better root out there. So we somehow eventually figure out which bridge has the lowest ID, and everybody agrees upon that. Okay. So these PDUs, bridge PDUs, are periodically broadcasted on all ports. So here we have 5 ports. So whatever is stored in here goes out on all of these ports. And then of course it comes in to all of these ports also. So what do we do when we get a PDU, say XRC? Suppose we get that on port Y. Then what we do then is we add the cost of the LAN for the LAN which is associated to this. So suppose here we have port number 5. I get the PDU that comes in here. Okay, and then I know I take that PDU and I add the cost of the incoming LAN to that. So I add add cost 1 to it, and then I compare that to what I have locally stored. If what comes in is better than I have locally stored, I replace what I have locally stored with this. Okay, first of all, we receive XRC on port Y. Then, if the LAN cost is 1, then I should compare XRC plus 1, and I should compare that with the stored PDU. And if the incoming one, when I added 1 to reflect the cost to reach me, if that's better, then I save it, and then I set Y to be the root port. Okay, because then whatever came in from here was better than I locally stored, hence this must be the root, right? Or this is my current belief that whatever is attached to this is the root. Okay, and therefore I update whatever is stored in here. And then I stop transmitting on that root port, because whatever I stored here, I don't need to transmit this out here, because then I only transmit when I think I have a better PDU than anybody else on that local area network. But here I know the root is here, so I don't need to inform it that that is the root. Okay, and eventually, it's not super clear now maybe, but eventually only the designated bridge will transmit BPDUs on the local area network. And therefore, we know, this one knows which LAN it is the designated bridge on, because that's the one that it's transmitting BPDUs of. And it also knows which port is the root port, because that's the port where it received the best PDU on. Okay, and then we're done. We have the designated, the bridge knows to which LAN it's the designated bridge on. It knows which port that is the designated port, and it knows which one is the root port, and we're done. Okay, And then to allow for this failure of machinery or putting in new bridges and so forth, then this best PDU which is stored in here has a timer associated with it. Okay, so suppose that this bridge knows that this one is the root, and the root keeps on sending its PDU on this LAN here. But if this fails, then there will be no PDUs transmitted over this one. And then the stored one here will expire and the process will restart, trying to figure out, okay, so the root died, which is the new root. Okay, so shall we look at a short example on how this works? Okay, so suppose we have a simple topology here with 3 LANs. We have one here, one here, and one here. Okay. And then we have 3 bridges. We have one which is connected here, and I wanted 4 LANs, so let's do this again. So sorry for this. So we have bridge 3 connected to these ones. We have bridge 2 connected to these 2, and bridge 1 down here. Okay. So now, just by looking at this, which one would be the bridge, the root bridge here? B1 is the root bridge, right? Okay, but at the beginning, when everything is powered up, all of them believes that they are the node. So bridge number 3 has ID 3. It believes that 3 is the root, and it has cost 0 to get to that. Okay, so this is the starting point for bridge 3. The starting point for bridge 2 is 2, 2, 0, right? It is 2, it believes 2 is the root, it has cost 0 to get to that. And bridge 1 has 1, 1, 0. Okay. So this is what happens at power up. Now, so let's see what happens when we start to transmit these PDUs. Okay, so they need to go in some order. So we can do this in any order. It turns out that the end result is the same. But suppose we start then by putting, okay, and what we do also is that we put all the ports in, they believe that they are the designated port. Okay, so, and why is that? Well, from perspective of bridge number 2, it believes it's the root. And therefore, all of its ports needs to be the designated ports, because there will be no other better bridge, right? So if you go back to a few slides, you see that this is the case. Okay, so this is the starting point. But now let's say that this PDU then goes out on the networks that it's attached to. Okay, so it's going to be a little bit messy now. But anyways, what happens is that this PDU goes out on the blue one and the green one, and it's picked up by bridge number 3 and bridge number 1. So let's see, what is bridge number 1 going to do? Well, it's going to compare its local PDU 330 with the incoming one, which is 2, 2, and then updated with the cost of going over the blue LAN, so it's going to be 221. Okay. We transmitted 220 and it was picked up here, and therefore the cost becomes 1 when it goes over the blue LAN here. So we want bridge number 3 needs to compare it with its current PDU and the one that it just heard, namely 220, but we add 1 for the cost of going over the blue one. Okay. So which one will win here? Which one is the best? 330 or 221? 221, right? So 221, okay. So, and the thing that happens also is that from bridge number 3's perspective, it knows now that this port is no longer the designated port, but rather the root port. Okay, because it heard that we can reach the root by going over this local area networks, and we can reach that with the cost of 1. Okay. Bridge number 1, however, will compare 221 with its 110, and 110 is going to win. Okay, so it doesn't do anything. Then suppose that this 110 is broadcasted out. Like this. It also goes down like this. Right. So what's going to happen? Well, now bridge number 2 needs to compare with the PDU it just received, which was 1, 1, and then adds 1 for the cost of going over the green LAN. So which one will win here? 220 or 111? Yeah, so 111 will win, and therefore this designated port here becomes the root port. Okay. What happens then? We keep on broadcasting this, but the interesting thing is what's going to happen when we broadcast this PDU over this LAN here. I warned you, it's going to be messy. So sorry for this. So what's going to happen now is that bridge number 3 needs to compare 221 with 112. So which one is going to win here?
One question.
Yes.
So it's supposed to be 212?
Here on the top here. Okay, so
Its own ID, the first one.
Sorry. Thank you. The own ID never changes, right? The only thing which is updated are the last 2 things. That is the current guess of the root and the cost to the root. So thank you. It should be 3 here, right? It's always 3 for bridge number 3. And here it should be also 2. It's always 2. Okay, thank you. Okay, but anyways, here what's going to happen now is that we get 3, it remains 3 here, but then we have root 1 and 2. Okay. So at this point, things have converged. Okay. For each LAN, we have a designated port and a designated bridge, and the correct ones. Each bridge has the correct idea which one is the root, namely bridge number 1, and it also knows the cost to get to the root. Okay, so for B3 it needs to go over this LAN, it needs to go over this LAN to get to the root. Okay, and now we're done. Okay, and Eventually, if something happens, a bridge dies, or we put in a new bridge, then the process is updated. And it's updated automatically. All right. Sorry for the extremely bad timekeeping here. But are there any questions before the break? That question guarantees that there are no questions. All right. Okay, so let's take 15 minutes.